Okay, so hi everybody. So let's see here. Okay. So this is lecture 25. And we're going to do two things in this lecture. So first, we're going to talk about inhomogeneous second order differential equations. So in other words, equations of the type T of y equals 0, T of y equals f, where f may not be 0. So in the previous lecture, we talked about T of y equals 0. And then most of the lecture is going to be about a generalization of everything we've done so far. So everything we've done so far is for one equation. You give me one differential equation, I find either a general solution or initial value problem. Now we're going to talk about what happens if you have a system of ordinary differential equations, but only in the first order case. So that means now you have multiple equations. You have multiple differential equations altogether. So this is like combining what we did in the beginning of the course, where you have a system of linear equations with what we were just doing now. You have a single differential equations. What if you have a system of differential? So let's start by doing item 1. So what did we do last time? Well, the setup last time was you're given an equation that looked like this. And we managed to turn this into some statement about a kernel of a linear transformation. So what was that? Well, there's a consisting of all infinitely differentiable functions from R to R. And then there was a linear transformation of this vector space to itself, defined by this equation. So and we studied two kinds of problems here. The first problem was the problem of the general solution, which is find the kernel of this linear transformation, which means find a basis for the kernel. And we showed that we could always do that by looking at the auxiliary polynomial and so on, and it was always a two-dimensional kernel. And the other thing which we touched on briefly towards the end was the initial value problem, which is find a particular solution in the kernel satisfying some initial condition. And we showed that this always has a unique solution. Well, we didn't show it completely, we stated it. Because the appropriate matrix that needed to be inverted was always invertible by this, Wronskian lemma, whatever. So now what we're going to study is the same setup, but now the right-hand side won't be 0, right? So now you're given an equation which looks like T of y equals f. So again, the T is the same as before. Okay, so the T is the same kind of transformation as before. But the difference is that this f may not be 0. Okay, oh, there's a question. So the question is, do the initial conditions always have to be 0? And the answer is no, they don't. So it could be at some number that's not 0, and the same thing works, actually. So the initial conditions don't have to be at 0. Another way of seeing this is that 0 is just as general as the general case, because you can change the variable by subtracting. Like if you want one initial conditions at 1, you can just study the function y of t minus 1, and then that'll turn the initial conditions to initial conditions at 0, and it doesn't change any of the derivatives. So you can reduce the general case to 0 anyway. Does that answer the question? Okay. So we're going to study the inhomogeneous case now. And again, you can ask the same two questions. What is the solution set? So what's the set of all solutions? And so the first question is, what's the general solution? And the second question is, can you solve the initial value problem? If I give you some initial values, say at 0. So right off the bat, we can say something about the general solution just because this is a linear transformation. Okay. So let's recall something from way back, which is that what does the solution set of AX equal B look like? That's an inhomogeneous linear system in numbers. Well, we showed a long time ago, and by now you probably know many different ways to see this, that this is actually just the set of solutions of the corresponding homogeneous equation, plus any particular solution to AX equals B. Okay. So for linear systems, the general solution always had this structure. Even if it was not homogeneous, the set of solutions always could be written as some particular solution, and then all translates of it by solutions to the homogeneous system. So the picture that goes with this is, a set of solutions to AX equals B looks like a line not going through the origin. The set of solutions to AX equals 0 looks like a line going through the origin. But this is and the difference between these two, you can get to any point in the inhomogeneous solution set by taking a point in the homogeneous solution set and moving along some particular solution, any particular solution, doesn't matter. So by the same reasoning, which I won't repeat here, at this point it should be an easy exercise for you to verify this. The same reasoning, really just based on the fact that it's linear, implies that the set of solutions of ty, where now y is a vector in this function space, that's the inhomogeneous system, that's equal to the set of solutions of p of y equals 0, which we already studied, plus any particular solution y. Okay, so these equations, they connect the inhomogeneous equations to the homogeneous counterparts, right? And the key thing that connects these two is this particular solution yp. So that's the new ingredient. That's a new thing we have to, we already know how to solve the homogeneous system. We did that earlier. The new thing we need to do is find out how to find this particular solution. So any questions about the setup? We'll now get into how to find that particular solution. Okay, so now the question remains, well, how do you find the particular solution? Well, again, the issue is you can't just use row reduction, right? If this was something in finite dimensional vector spaces, you could choose a basis and do the correspondence principle and use row reduction, right? So can't use correspondence principle plus row reduction because F is infinite dimensional. So that's the new twist. We cannot use our existing methods. And so it turns out that in general, it's actually pretty hard to find a particular solution. And we won't discuss how to do it in general for any F. What we'll do instead is study, well, how do you solve this for some very particular right-hand side F? And these are still, this is still useful because many of these kinds of F often come up in application. So I'm going to illustrate this with an example. Here's the example. Here's the equation, y double prime plus 2y prime plus y equals t squared. Right, so these are all functions of t. Okay, that's not very readable. Okay, that's the equation. And in this equation, this is a new ingredient, right? This is the f. That t squared is viewed as a function in a vector space of differentiable functions. Right? So in this case, corresponding operator is d by dt, d squared by dt squared plus 2d by d plus identity, which is otherwise just known as d by dt plus identity the whole squared. You can just sort of see it. Right? It's the formula for a plus b squared. So, well, okay, how do I find this particular solution that gets mapped to t squared? Right? So I have my t that gets maps f to f. It hits this particular point that I care about, which is t squared. And now I'm interested in finding a point. I'm finding some function where this came from, right? And the reason I'm stuck is that, well, f is this huge vector space, and I have no idea where it came from. So what's the idea? Well, the idea is well, it's kind of, it's not as systematic as the other things in this course. The idea is make an educated guess about where these, about what the solution. So what do I mean by that? Well, based on the right-hand side. Okay, so what is this equation saying? It's saying that there's some function. So when you differentiate it twice, and then you add twice its derivative, and you add the function, you get t squared. Now, t squared is a very particular kind of function. It's a polynomial, right? So the question you should ask yourself is, what functions differentiate? What functions differentiate to polynomial? So, if you had to guess, what this y was, yeah, just polynomials, right? The functions whose derivatives are polynomials are, well, they're polynomials. The integral of a polynomial is a polynomial. Well, the answer is polynomial. Can I say something a little bit more? So do I have to consider really all polynomials if I want to find out a solution to this differential equation? The right-hand side is actually a polynomial of degree 2. So here's a better answer. What somebody said in the chat, you can consider polynomials of degree at most 3. Okay, that's a good thought. Why did you say 3? You can unmute and say.
I said 3 because because you can assume that the lowest derivative which you're taking, which is the first derivative. Wait, actually, now that I think about it, you could take the second derivative of a function, or sorry, no. The first derivative of the function is, like you could say, is t squared, so it would have to be degree 3. And you know that y and y prime can't be 0 because then the lower derivatives would also be 0. So you can kind of narrow it down that way.
Okay, so good. So you said it'd have to be P3. But you can do a little bit better, what somebody suggested in the chat, which is actually you can do degree 2 polynomials. And the reason you can get away with degree 2 polynomials is, well, look at this equation. It has a y of t term. Now, if you plug in any polynomial of degree bigger than 2, that y of t term is going to preserve the degree, right? So the circled term actually, and the other terms are going to have only lower degree because they're derivatives. So the circled term implies that y must have degree less than 2. If there's a polynomial solving this equation, it must have degree less than 2. Right? Now the key was that there's this term that doesn't get differentiated at all. Okay. And somebody asked a question, can you have e to the polynomial of something? That's a great question. We're not proving here that polynomials are the only solution, right? Maybe, right now, maybe there's all kinds of other crazy functions that solve this equation. We don't know, right? So the question was, can we have e to some polynomial and t? Maybe, I don't know. I don't know how to answer that right now. We'll see what the answer is later. But now, the idea is, I mean, this is why it's a bit of a leap of faith. Now we're going to make something that's called an ansatz. So, okay, I'll just write it here. So this is a German word that means solution form. Okay. And really the way I like to think about it is it's a leap of faith. Okay. We're going to say we don't know what the answer to this is, but imagine for a moment that the answer wasn't P2, right? Let's look for answers in P2. Okay. So so I'm not claiming that the answer has to be in P2, but I'm saying assume for a moment that the answer is in P2. And then solve for it. If the solution works, then you got a legit solution, right? That's why it's a leap of faith. We don't know it's going to work yet. But if it does work, then okay, it worked. Right? So let's now do this for this particular problem, right? Okay. So what's our equation again? Our equation is y double prime plus 2 prime plus y equals t squared. So I'm going to assume y is in P2, which now is a familiar vector space, right? Right? Okay. Now, if that were the case, well, what would the solution look like? Well, this implies, now these are unknown, right? Well, what would the solution look like? Well, I would differentiate this thing twice, right? So, so the second derivative of this is 2 A2 plus, now what's the first derivative of this? Twice the first derivative, so the first derivative is going to be A1 plus 2A2t. And now what's just the function? Well, it's just this. So if you assume it's ansat, then this is saying that the equation must look like this. Okay. But now if you match the coefficients of, these are two polynomials now, right? Of t to the 0, t to the 1, and t squared. Well, you're going to get three equations, right? One for each of these coefficients. So let's write this in matrix notation. So on the right-hand side, you have, okay, so the first row is going to be, the coefficient is going to correspond to the constant term. So the constant term on the left-hand side is going to be 1, 2, 2, and on the right-hand side is going to be 0. And the coefficient of t on the left-hand side is going to be, so I'm looking at the coefficient of t and, how expressing it in terms of variables a0, a1, a2. The coefficient of t on the left-hand side is going to be 0, 1, sorry, 1, a1. And then a2 is going to have a 4. And now what's the coefficient of t squared on the right-hand side? That's just 0, 0, 1. On the left-hand side. Now the right-hand side is just 0, 0, 1. Okay. So the point is now you just get a linear system. And okay, it has 3 pivots. It's already in row echelon form. You solve this. And in this particular case, the answer you get is, what do you get? You get a0 equals 6, a1 equals -1, and a2 equals 1. But this is the point, right? Like you made this leap of faith, but now you actually have a solution in your hand. It satisfies the equations. So it works. So that's a particular solution. So what does that imply? It implies that if you take the particular solution, 6 minus t plus t squared, this solves the equation, t of yp equals t squared. Okay, so this is something, this is a lowbrow way of saying something which we can say a bit more abstractly, which actually clarifies what's going on. What's really going on is you had this t going between these two big vector spaces, right? Vector space F2 itself. You had this t squared, and we said, hey, we think that there should be a solution in this much smaller vector space, P2. And so really what we did is we consider the restriction of t, let's call it t hat, from P2 to itself. Oh, did somebody say the answer is not correct? Okay, let me finish this. Ignore the details for now, but let's check in a moment. We considered the restriction of this thing to itself. And now the point is these things are finite dimensional. Right? And so then you can solve some linear system of this in some basis, which you were doing for a while. And that's exactly what this is. Okay, so T hat is this little restriction that only looks at P2, maps P2 into P2, and now everything becomes finite dimensional. And then you do row reduction. That's a more abstract way of saying what's on the left hand side. Okay, so somebody said the answer is wrong. Okay. Let's see what the mistake is. So okay, I compared the coefficients of compared the constant terms on both sides. Those are correct. I compared the coefficient of t on both sides. Those are correct. I compared the coefficient of t squared on both sides. Those are also correct. Did I not solve the linear system correctly? Is that okay? A2 is 1. That's correct. A1 is oh whoops, -4. Okay, thank you. Yeah, thanks for pointing that out. -4. Okay. So actually the solution is this. Okay. And okay, just to make sure, let's plug this in and make sure it's correct. So now, well, okay, I don't want to write this here. Okay, fine. Let's just check, right? So what is the second derivative of this? The second derivative is 2, right? The first derivative is -4 plus 2t, and the no derivative at all is 6 minus 4t plus t squared. And what is this? Yeah, indeed, everything cancels out. Okay, good. So that's it. So this is actually a very simple idea. We could have done it before the first midterm. I mean, but really what's going on is you restrict to a finite dimensional subspace. This has a fancy name. It's called the method of undetermined coefficients. And you'll do many homework problems solving these kind of problems. Now, what's true in general? I'll just state it, what happens in general. Or actually, wait, let me finish that problem. So in this problem, what did we just do? We found a particular solution, but we still didn't find the general solution, right? So what is the general solution now? Okay. Well, remember, to find a general solution, I also need to find the solution to the homogeneous part. Also, the kernel of P is what? Well, the operator was d by dt plus identity squared. So the auxiliary polynomial was just r plus 1 squared. And so this is just going to be e to the minus t and p e to the minus t. Okay. So now I go back to what I did on the first, what I said on the first slide here. Right. The solution set of the inhomogeneous system is a particular solution plus the solution set of the homogeneous part. So the general solution is actually this particular solution. So 6 minus 4t plus t squared plus any multiple of these okay, where these are real coefficients. So by the way, it's revealed that actually your hunch was correct, right? There are solutions of this linear system that are not polynomials. There are solutions that have some polynomial and some exponential in them. And the reason is that these exponentials get killed by t anyway. So it still solves the equation. These are the only solutions, yes. So the reason for that is that the solution to the homogeneous part, the only solutions are what's written here. And this relationship here, which says same reasoning, that's an equality. So these are the only solutions. you can, so these are the only solutions. Okay. And now you can combine this with how can we prove these are the only solutions? Well, I'm going to leave that as a homework exercise. So it's before the chapter 4 kind of exercise. I'm not asking you to prove that the kernel of T is the exponentials. We're not proving that in the course. Okay. So so that's the general solution. And now if you have this additional twist, if you have an initial value problem, so you have some further initial condition. I don't know, let's just plug in some numbers. Did I prepare numbers? Okay, I'll just make some up. Then, okay, it's the same principle. You have to solve for these C1 and C2, right? So we'll solve linear system. So what's the linear system? Well, so let's call these solutions, let's call this Y1 and let's call this Y2. So you need to solve Y1 prime, Y1 at 0, Y1 prime at 0, Y2 at 0, Y2 prime at 0, C1, C2 equals Y0, Y1, but now you have to correct this, right? Because there's an inhomogeneous part. So actually you have to subtract off YP at 0 minus YP prime at 0. So there's this contribution of the inhomogeneous part, right? That comes from the particular solution. And this, I mean, there's nothing new. There's the same, the only thing that changes is the right-hand side. And so this matrix is always invertible by this, Wronskian, which we didn't prove and won't prove. Okay. So once you have the general solution, the initial value problem works in the same way. So I'm not gonna do the calculation. This is something that's actually very simple and best learned by just doing the homework. Okay, so what can we say in general? All of this was to just solve one particular right-hand side of T squared, right? What can you say in general? T of y equals T to the M always has a solution in polynomials of degree at most M. And what that means is you can find by solving a linear system. By which I mean a particular solution. Okay, this is always true. You can prove this, the proof is given in the book, but I won't do it in the class. It's just it's quite a simple proof. And so that's one thing. Another thing I want to say is that can do something similar. For T of y equals a sine or a cosine. And here, the natural restriction, okay, which functions differentiate to sines and cosines? Well, sines and cosines, right? And again, this I'm not going to discuss in class. Same idea, you can do it on the homework. And this is a whole industry, okay? Like there's a whole branch of math related to this where for different classes of F, you guess the right subspace, make the ansatz and make it a finite problem. So we will skip other right-hand side. Like, in the book, you can even do, I don't know, t to some power, e to some power, cosine to some power, beta t, etc. Because I think it's just ugly and it's not, it doesn't really add anything in terms of understanding. Okay. And one more important remark, which again will be best learned doing the homework. How do you solve t of y equals, let's say you have a sum of these things. So t squared plus 3t to the 4. How would you find a particular solution to that system? Any thoughts?
Same way, but degree 4.
Yeah, so one way is same way, but P4, that'll work. Somebody else suggested another idea, which is break it up into 2 linear transformations. Find a particular solution for each. So that solve t of y1 equals t squared, t of y2 equals 3t to the 4, or, okay. And now just add them, right? You get t of y1 plus y2 equals the sum. Okay, and this trivial fact, which we could have done after the first week of class, is known as the superposition principle. It's a very important feature of differential equations is that they're linear equations. So you can always break them up like this. And that's all there. There's a whole section of the book called superposition principle, but it's really just linearity. So these I don't want to dwell on. It's like one of the easiest things in the course, but also one of the most boring. What I will do is organize. We covered a lot of different little things in this section of the course. I'll try to organize all of them on one slide, because the most common confusion in this part of the course is that there are too many little things and they get confused. It's not like any of them is particularly hard. So here's a summary. So this is the so given some second order differential equation, possibly with initial values. Here are the ways in which linear algebra was used. There are 3 different ways. I just want to separate them because often people get confused between these 3 different ways. So the first important fact is that the set of is that the set of solutions of the homogeneous equation is just the kernel of this t, right? So t is a linear transformation from f to f. And then the way we found this is you reduced to first order ODE by factoring t. Just a second. by factoring t into first order operators, right? And this, this factoring used some, like, it used this auxiliary polynomial, and it used this like algebra of operators. So this was a new, quite powerful idea in linear algebra, that just as you can do algebra with matrices, you can also do algebra with operators. And once you do that, you get something out of it. And we concluded that this is always some two-dimensional subspace. So that was the first thing we did. And here we made heavy use of properties of linear transformations, kernels, etc. The second thing we did, which it's really the last thing we did, but the second way in which linear algebra appeared is that the set of solutions of the inhomogeneous equation is always the kernel plus a particular solution. And we found YP by restricting E to finite dimensional subspace, such as polynomials of F, and then doing row reduction. Okay, so this is a different way in which linear algebra appeared, right? In the inhomogeneous equation. First of all, it allowed us to relate the solution set to the homogeneous solution set. And then it allowed us to do this, undetermined coefficients. And then the third way that linear algebra appears is in solving the initial value problem, right? So, so the abstract way of saying this is that the map that maps the kernel of T, so the solution set of any homogeneous second order ODE to R2, and then this implies that these linear systems always have a solution. Sorry. Okay. And the net conclusion of all of this stuff is that the initial value problem for second order ODE always has a unique solution. Okay, so this slide is kind of important just to organize your thoughts, because there are a lot of different parts. Okay, there's a question. In general, for differential equations in the real world, is a method used to find a solution mainly guess and check like we are doing? So it depends. In full generality, yes. There's no general way to solve partial differential equations, for example. There's a huge area of math devoted to solving very specific partial differential equations. It's really hard. For ordinary differential equations, there are some general methods that we'll touch on at the end of the lecture. But yeah, if you look at differential equations as a whole, a large part of it involves identifying these finite dimensional subspaces that will contain the solution. Yes, thank you. I made a mistake. This should be y1 prime. Thank you. Okay, so that finishes second order ODE. I'm now going to move to systems of ODE. So what's a system of ODE? Well, it's a bunch of equations, each of which is a differential equation. For example, find two functions x1 of t and x2 of t satisfying, I don't know, x1 prime equals 5x2 minus, I'm sorry, yeah, sure, let's leave it at that. And x2 prime equals, I don't know, 3x1 minus x. That's just some example I just made up. So now what are these? These are unknown functions. Okay. And now you have two equations, not just one, or many. We'll have a general setup in a moment. But all the derivatives are first order. Okay. So that's what. So now let's set up some good. So by the way, I'm using x instead of y just because the book uses x instead of y. There's no essential difference, right? I'm only using the variable letter x because the book uses that letter. It's the same concept. But now the difference is there are more equations. So let's okay. So first, I'm going to, instead of thinking about a bunch of different functions, I'm going to put them all in a vector. I'm going to define the vector space f to the n. That's a vector space of vectors whose entries are functions. Okay, this might blow your mind a little bit the first time you see it. Already, each of these things is a function, which is a pretty big object, but now you have a vector of functions. It might blow your mind a little less if you just look at some examples of what's in here. So for example, here's an element of F2. It's a vector, each entry is a function, not a big deal. You can also think of this if you prefer, and of course, you can also think of it as the set of vector valued functions. X underline means a vector value. And what that means is a function from R to Rn, infinitely differentiable. Right? So you can think of even this in two different ways. You can think of it as a vector, and each entry is a scalar function. Or you can just think of it as a vector valued function, right? It takes a number t and outputs a vector in R2. So this is a vector space with entry-wise addition and scalar multiplication. Okay, so any questions about this vector space? Okay. Now let's look at some linear transformations on this vector space. Well, one very simple one is differentiation. And the way that's defined is you just differentiate every entry. For example, if you differentiate this function, which is sine and cosine, this vector valued function, you just differentiate every entry, you get this other function, this other vector valued function. So that's a linear transformation on this Fn. It says entry-wise addition and scalar multiplication. Okay. Here's another linear transformation. If you have some matrix A with columns A1 to AN, let's say n by n, then you can define AX to be a new function, AX of t, just as you would if it was a regular vector, right? So that's going to be A1 times X1 t. And again, maybe best given with an example, I can multiply, let's say I have some matrix 1, 2, 3, 4, and I multiply it by this vector sine t cosine t. I get a new vector valued function, which is sine t plus 2 cosine t. And here I get 3 sine t plus 4 cosine t. Okay, so let that sink in. We have these two quite different kinds of linear transformations on this vector space. One is just good old matrix vector multiplication, but now the entries are functions. Okay, it works the same way. And the other is differentiation. Okay, any questions about this? Okay. So now I'm going to define a particular type of first order ODE, or just a particular way to format it. So let me make the definition. System ODE is in normal form if it is written as x prime of t equals a x of t plus. Now, what are the types of all these objects? So these are both my unknown vector valued function. This is some known, like right-hand side, also a valued function. And this A is just an n by n matrix with real entries. Okay. So that's the kind of equation we're going to study. Now, if I go back to the previous slide, the thing in the upper right corner can actually be written in this form, right? This can be written as, let's do it here, x prime of t equals a x of t, where A is the matrix. Well, x1 prime, so the first row, that's going to be 0 and 5, because it's just 5 times x2, and there's going to be 3 and minus 1. So that's the kind of equation we're going to study. And I should say, I mean, this is just the same thing as d by dt. Right? D by dt is a linear transformation. on these vector valued functions. Any questions about the equation? Okay. And again, it's going to go the same. We're going to ask the same questions. So this is called homogeneous if this F is 0 and inhomogeneous otherwise. And we'll study this first. In this lecture, we'll only study the homogeneous. So any questions about this? The two questions we're going to ask are, what is the general solution? Sure, I'll write a little slower. The second question is, find a solution x of t satisfying some initial conditions. Or maybe let's, what letter do I want to use for the initial conditions? I'm not sure what the book uses, but let's just call it this for now. Yes, yeah, sorry, the handwriting has gotten bad. I'll write more slowly now. These are the two questions. So we're going to fully answer the first question in this lecture. And then we'll get to inhomogeneous and IVP and all that stuff, just as we did. And this has, by the way, very cool applications, which I'll get to at the end of the lecture. Okay, so let's now look at some examples and how to solve. Okay, here's one example. So these are two equations. And in vector form, this would be written as x of t equals the matrix 3, 0, 0, 5, right, prime, times x of t. Okay. So that's a very simple example. And what's very nice about it is, well, the variables don't really interact, right? The first equation is about x1. And the second equation is about x2. So I can just solve these separately, right? So the word for these are decoupled, which means really they're two separate equations and separate variables. They have no interaction. And so I know how to solve these, right? So I get the solution. Well, x1 is just of t, that's a function. They're just exponentials, right? This is like the first thing we did in differential. Okay. And so, well, the general solution is just any two functions like this for any C1 and C2. Right? But now let's write this in vector notation. In vector notation, really you have a linear transformation from Fn to Fn defined by t is d by dt minus this matrix. And the general solution is the kernel of this T. So it's a set of all vector valued functions with 2 entries that are in the kernel of this, right? Because being in the kernel is the same as satisfying the equation. Satisfying both equations, that's the key. And that is going, according to what we calculated, it's a set of all things that look like this. And so that's, is that that's a subspace. Can anybody find a basis for that subspace? Anybody know what a basis for the subspace is?
Just multiples of that vector.
Okay, so which vector? So I can multiply the 2 coordinates by different numbers, right? So it's not just multiples of that vector. So somebody proposed the answer e to the 3t and e to the 5t. That's not correct, right? Because those aren't even vectors in F. I'm sorry, in F2 in this. The correct answer, which was written last in the chat, is it's a span of e to the 3t 0 and 0 e to the 5t, right? Because if I take all linear combinations of these 2 vectors, I'm going to get everything that's written over here. Okay. Okay, so somebody asked the question, can you explain again how the vector notation got the n by n matrix? Well, there's just a 2 by 2 matrix here, right? So because this equation, let me just write this equation in a way. This is just saying d by dt x of t equals a x of t, or a equal to this 2 by 2 matrix. And then if I rearrange it, I get this. Does that explain? Okay. So that was a simple example, and really it seems like a bit of a waste, right? Like we developed all this fancy notation, we talked about these like big vector spaces, but in the end we just solved 2 little first order ODE, which we could have done like math 1 here. So let's look at a more interesting example where really now the power of linear algebra will come out. So here's the example. I have y1 prime, I'm sorry, x1 prime. Equals, or let me just write the t's actually, just remind us of their functions. I'll eventually stop writing the t's. Equals 2x1t minus 2t. Sorry, x. Okay. Now, in normal form, this is x, d by dt of x of t equals ax for a equal to this matrix of coefficients, right? So 2 minus 1, 3. But this is more interesting, right? I cannot separate these equations. Both variables occur in both equations. These are really 2 differential equations that are interacting in some way. Cannot isolate them. as opposed to the previous system, which was decoupled. So how do I solve this? So this is, it's not at all clear how to solve this a priori. Now the idea is, well, would be nice if it was diagonal, right? If it was diagonal, life would be easy, right? I know how to solve diagonal. The key is, the reason this is decoupled is that this is diagonal. So the coordinates don't interact. So what tool do I have to make a matrix, square matrix diagonal? Well, diagonalization, right? So idea, I reduce to the diagonal case via diagonalization. So let me be very concrete and just work this out for this example. Okay, so let's diagonalize A. Okay, so what are the eigenvalues of A? Well, I have determinant of 2 minus lambda. So what is that? That's minus 2 plus lambda times 2 plus lambda plus 4. Oh no, plus 3, sorry. Which is otherwise known as lambda squared minus 4 plus 3, which is lambda squared minus 1. So the eigenvalues are plus or minus 1. What are the eigenvectors? Okay, let's give these names because they're going to matter. So lambda 1 equals 1, lambda 2 equals 1. I'm not going to do row reduction here, but we all know how to find eigenvectors at this point. The corresponding eigenvectors are v1, which is 1, 1, and v2, which is the vector 1, 3. Okay. Okay, so what did this get me? Well, the key observation is if I hit an eigenvector with A, it just acts like a scalar, right? That's what an eigenvector is. If I multiply an eigenvector by the matrix of which it's an eigenvector, it just gets multiplied by a scalar. So let's consider the function e to the lambda 1t times v1. Let's call this x sub 1. Okay. Or well, okay, I don't want to introduce this notation. Let's just call it this. Now, what does the let's just see what the equation does to this vector. You have A times e to the lambda 1t v1. Well, this is just a number. This is e to the lambda 1t times a v1. But aha, it's an eigenvector, right? This just becomes e to the lambda 1t lambda 1 v1. Okay. But now, does anybody see what to do in the next step? So I'm interested in finding solutions to this equation, right? What I'm doing right now is computing the right-hand side of that equation. I'd be really happy if it was equal to the left-hand side, right? Can anybody see if that's the case? Like, what is this? That's a derivative with respect to t. And this v1 is a constant, so actually that doesn't change anything. So this is just this. So actually this function solves the equation. And the key thing that happened, the reason you shouldn't be surprised is this. I'm sorry, is this. This is a key step. The key step is that if you look at functions that are multiples of an eigenvector, this just becomes a 1D first order differential equation, right? So A acts like scalar multiplication on, well, on functions that are multiples of eigenvectors. So similarly, what happens with the other one? Well, this is a scalar. But now the key is use the eigenvector equation, right? This is e to the lambda 2 e lambda 2 v2. And that is just the derivative of this whole thing. And so what's the upshot of all of this? Well, the upshot of all of this is that we found two solutions, which we'll check are linearly independent, to this equation. So what are those in this particular example? Those are e to the t times 1, 1. The other is e to the minus t times 1, 3. Okay. So again, beyond the scope of the course, you can show these are the only ones. Okay, so the beauty is, if you, I mean, there are two different ways of interpreting this. One is you just change the basis to be the eigenbasis, and then every matrix becomes diagonal. But you don't even have to do it explicitly, right? If you just, I mean, write the, I mean, here's another way to view it. Suppose you search for solutions of d by dt, x of t equals ax of t, of the form x of t equals some function. So what should we call that? Let's say g of t times an eigenvector. Well, then what does it look like? Then the equation becomes A g of t v equals d by dt g of t v, but this is now just equal to lambda g of t v because it's an eigenvector. And this is a one-dimensional ODE. Okay, so if you look for solutions that are multiples of eigenvector, there's a really easy problem. Now the upshot of this is that if you have a basis of eigenvectors, you will get n linearly independent solutions, and then it can be proven those are all solutions. So here's a general theorem. If A is an n by n matrix, is diagonalizable, let's say with eigenvalues lambda 1 through lambda n and eigenvectors v1 through n. Let's say for now real, we'll deal with complex in the next lecture. Then the following functions, e to the lambda 1t v1 all the way up to e to the lambda n t vn are linearly independent solutions of x prime t equals ax. And actually, okay, and they're a basis for all solutions. Okay, so this is the beauty of diagonalization. It turns an n-dimensional object into a one-dimensional object. We won't discuss the non-diagonalizable case. I mean, there's a way to do that too, but we won't do that in this course. But this is a very good thing, right? And if you have a diagonalizable matrix, for example, if it's symmetric, right? We know symmetric matrices are diagonalizable. Then you always are in this situation where you always get these solutions. Now, I will end. Okay, I won't cover any more material. Are there any questions about this general theorem? Okay, well, I do want to show you one cool thing, which is why are we doing this? We'll do this in the next lecture. The first is you can solve any, or you can reduce any higher order ODE, which means involving any number of derivatives to a system of linear first order ODE. Okay. So what that means is if you have a single equation, like let's say y triple prime minus y double prime minus y 0, say, okay? That's one equation, but with very high derivatives. You can always reduce it to a system of first order ODE, which we just learned how to solve. And the second thing, which I'll elaborate next lecture, is you have many physical applications, which is spring mass systems. So I'll just end with an animation. So so in the previous lecture, we looked at this spring simulator, right, with one spring. One thing that comes up a lot in engineering is the next tab, which is this. What if you have two masses with springs? right? So you can imagine that this is important. And I mean, this is the basis that forms how you study vibrating strings and all sorts of other things. And you can solve this easily, again, by reducing it to a system of first order ODE. It's not obvious at all. I'll do that in the next lecture. But yeah, that's the end of the lecture. Any questions?
You have a question about, like, you said that the motivation is that you can use this to solve any higher order ODE, but how do you separate, like, because like the example you have showed us is only about like first order ODE or something.
Yeah. So I didn't tell you how. So there's this amazing trick that allows you to reduce any order ODE to a system of first order ODE. I have not shown you that yet. It's not obvious. I'll do it in the next one.
That is me, and also like the reason that why you can solve system of ODE like this is because of you find the eigenspaces of A. Also, it also matches with the eigenspaces of function space.
Yeah, exactly.
Corresponding.
Yeah, the reason you can easily solve many systems of ODE is you can do diagonalization, right? Otherwise, it's not clear how to separate that out into 1D equation.
Yep. Thank you.
Yep. Go back to the last slide with content, yes. So this, by the way, we'll do next time. So let's see. So some people had some questions. With diagonalization, can you solve any order ODE technically? Yeah, it's very powerful. If you combine these two facts, can solve any homogeneous ODE of any order, including second order. This actually gives an alternate way to solve second order. Okay, the previous slide. Yes, this slide. Yeah, it's super cool. I agree. Great. Well, thanks.